The universe has been the subject of man's curiosity since he learned to walk upright. The need to expand has progressively led him toward a science that might someday find him walking on planets millions of miles beyond his own. The evolution of the spaceship spans the ages. History traces the birth of rocket propulsion 10 centuries back to China. The next 1,000 years saw the growth of spaceflight concepts in theory only. Galileo, Kepler, Newton, and others contributed one by one a basis for the equations of a 20th century rocket technology. In the early 1900s, America's Robert Goddard fired the first liquid propellant rocket. But only a few noted this accomplishment with more than passing interest. Among those who did were the Germans. And at Peenemünde in 1942, the liquid chemical rocket was transformed from a laboratory curiosity to a large-scale guided missile after many spectacular failures. America's first serious and promising entry in 1948 was the Convair MX-774. It resembled V-2, but introduced the swiveling rocket chamber, integral fuel tanks, and separable nose cone. Again, interest was limited, but private industry persevered to bridge the gap between those early times and the challenge of tomorrow. 1957. The bridge was the United States Air Force Atlas. Like V-2, it was born of a need for military power. Its role as a spacecraft booster was inevitable, but not immediately apparent. The Atlas succeeded, but only after 2 attempts that made some feel the project was a failure. Less than 5 years later, more than 125 launches had made Atlas operational as a weapon, as a booster for instrumented space probes, and as a launch vehicle for our astronauts. Now at Cape Canaveral, a 17-story gantry rolls back to reveal the first transition from missile to advanced space technology, a test bed for the coming generation of hydrogen-using space vehicles. This is Centaur. Its booster, a modified Atlas D. The upper stage, an extension of the Atlas structural design, but filled with liquid hydrogen, a fuel that boils at 423 degrees below zero at sea level pressures. A fuel that delivers more energy per pound than any other liquid propellant known. Flight test for Centaur, May 8, 1962. Some who had watched in 1942 and in 1957 were again on hand for this one.
we were all very disappointed in the untimely end to the Centaur flights. Nonetheless, we certainly can't say that we're discouraged about it. We'll find one thing which is encouraging. As you know, this is the first of a planned series of 10 test flights, the purposes of which are to determine what is not perfectly right about the vehicle and provide the information necessary to make improvements to bring the vehicle up to the standard of reliability and performance which is necessary for its operational missions in the future.
The Centaur project was officially launched in the fall of 1958. By direction of the Advanced Research Project Agency, the Air Research and Development Command awarded General Dynamics Astronautics a state-of-the-art development contract based on minimum initial funding. Program sponsorship was later transferred to National Aeronautics and Space Administration Headquarters, Washington. In July 1960, the program was placed under direction of NASA's Marshall Space Flight Center, Huntsville. And in October 1962, with its Lewis Research Center, Cleveland, Ohio. The challenge was to build a hydrogen-fueled spacecraft, taking every possible advantage of Atlas fabrication techniques, existing tools, and off-the-shelf hardware. By now, the company had financed a study of many high-energy propellant combinations for practical systems development and mission capability. Hydrogen provided the greatest gain, and development of this technology was the primary goal. The oxidizer used in Atlas, liquid oxygen, was now well developed and thus preferred over other chemicals with slightly higher energy potentials. A small increase in specific impulse did not warrant the time-consuming and expensive development of a second new technology and could have compromised the program. So the oxygen-hydrogen combination was born. Pratt & Whitney Aircraft was named associate contractor. They had already tamed the tricky but potent hydrogen on an industrial scale. Now they would produce an engine that could handle it. Government, science, and industry joined in the drive to lay the foundations on which Centaur and her followers would depend. The advantages of liquid hydrogen for extended space flight far outweighed the fact that a long-term pioneering effort would be required to learn how to work with it and then build the facilities and systems geared to its use. In its natural state, hydrogen is a colorless, odorless gas. The first step, learn how to convert it to a workable spaceship fuel. Learn how to refine it from crude oil. Learn how to clean it, weigh and measure it, cool it, store and transport it in enormous quantities. Study its characteristics. Explore the potential hazards that might occur under certain conditions. And develop the vacuum-insulated lines to carry it with mobile tanks to store it in its supercooled state. Next, create the airborne hardware that could withstand not only the piercing chill of hydrogen, but a wide range of opposing temperatures as well. The need for special hydrogen boost pumps was met by the early experience of Borg-Warner's Pesco Products division. This high-speed system eliminated the need for high Centaur tank pressurization to force propellants to the engines. Pratt & Whitney proceeded with development and testing of the free world's first hydrogen-using rocket engine. Producing 30,000 pounds of thrust, the dual propulsion system has a higher specific impulse rating than any of its forerunners. There were problems, and there were solutions. And 3 years after its inception, the RL-10A1 engine passed its official preliminary flight rating test. 20 successive firings, equal to 6 Centaur missions. At General Dynamics Astronautics, early research revealed what hydrogen would do to the materials it would. Tests like this determine types of materials and manufacturing techniques required for basic vehicle design. Like Atlas, Centaur is made of lightweight stainless steel, has no internal bracing, and is pressurized with helium to retain its shape. The 42-foot-long, 10-foot diameter Centaur consists of a hydrogen tank and an oxygen tank. Inside, a double insulation bulkhead separates the tanks and forms a heat barrier between the two liquids, which differ in temperature by 126 degrees. Another type of insulation protects the payload and tank from heat and air loads until the vehicle reaches an altitude where the air is thinner and friction is no longer a problem. At NASA's Langley Field, Virginia Research Center, the insulation panels more than proved their strength under Mach 3 winds. This panel, mounted on a fixture that simulates Centaur's hydrogen-chilled walls, withstood dynamic pressures from 1,500 to 5,000 pounds per square foot, and temperatures ranging from 300 to 600 degrees Fahrenheit. Such environments are much more severe than those expected in flight. And at Astronautics Point Loma laboratories, the panels were subjected to in-flight jettison tests to assure that they would separate from Centaur's ice-coated structure. Nose fairing release was also duplicated under the actual gravity forces and dynamic air pressures expected in flight. This full-scale facility was used to develop the propellant loading system for Centaur's Cape Canaveral Launch Complex. Tests here enabled astronautics engineers to study various insulating schemes and the density characteristics of liquid hydrogen. This marked the first mass use of hydrogen in a thin-walled tank in the United States. Since zero gravity is the relatively unexplored environment where Centaur and other advanced space vehicles will operate, studies in this field took on major national significance at the start of the Centaur program. How would liquid and gaseous hydrogen react to weightlessness? Would the liquid be in the right position for main engine start after unpowered flight? What would solar heat do to the subcooled propellants? What kind of hardware would be required to sense and control these conditions? Analytical theory was not enough. Prolonged conditions of weightlessness would have to be duplicated to find the answers. Producing zero-G on Earth presented problems. Drop test facilities at astronautics could only create up to 2 seconds of weightlessness. Between 1959 and 1961, the Air Force's Wright Air Development Command at Dayton supported astronautics in an intensive program of zero-G flights. Using first a C-131B aircraft and later a KC-135, this team flew over 1,200 parabolic maneuvers, achieving zero-G durations of from 1 to 18 seconds. Early test capsules scaled down to represent the Centaur fuel tank contained liquid nitrogen. Later, approximately 200 maneuvers were flown with liquid hydrogen. High-speed motion picture cameras recorded a wealth of information on liquid distribution during weightlessness and the effects of external heat on hydrogen. These tests determined the amount of venting required to keep internal tank pressures at a minimum and formed a basis for development and proof of sensing equipment to reveal the position of liquid and gaseous hydrogen during flight. At NASA's Wallops Island Station in Virginia, Aerobee rockets achieved up to 4 minutes of weightlessness for hydrogen-filled capsules carrying Centaur instrumentation. Later, scale models duplicating the Centaur tank and containing fluids that simulate liquid and gaseous hydrogen were developed to provide longer-lasting zero-G conditions for laboratory tests. For an inside look at propellant behavior during an actual Centaur flight, Palomar Electronics produced the first known airborne television system of its kind. Based on studies for Project Mercury, Bell Aerosystems provided miniature hydrogen peroxide rockets to keep Centaur and its propellants properly positioned during zero-gravity maneuvers. This system is complemented by the astronautics autopilot and sun-seeking equipment for vehicle orientation. To evaluate the ability of these combined components, astronautics engineers constructed a coast phase test stand at their Point Loma site. The bearing center of this 3-ton simulator floats on a frictionless cushion of air and duplicates the motion of Centaur in space. Mounted on the stand, the control rockets, autopilot, and sun-seekers prove their ability to orient Centaur in pitch, yaw, and roll. The development of ground and airborne telemetry called for still another pioneering effort. The equipment would have to be designed for an exchange of information over great distances. Airborne instruments, more in number than for any other spacecraft, were designed not only to withstand the extremes of space, but to operate for extended periods of time on minimum power and relay the data so vital to advanced research. The complexity of Centaur's missions called for a new generation in guidance. Minneapolis Honeywell developed a miniature self-contained system capable of directing the vehicle into one of the most difficult maneuvers known, a 24-hour orbit 22,000 miles above the Earth. As the first flight vehicles went into production, full-scale systems tests began at astronautic Sycamore Canyon site. A heavy Centaur tank, known as the propulsion test vehicle, was equipped with experimental engines and related systems. On January 5, 1961, during a test with hydrogen to determine the proper engine starting sequence, fire broke out near the hydrogen boost pump and fed on the insulation encasing the vehicle. Hydrogen leaked from a duct between the pump and the engines and was ignited by heat from the turbine which powers the pump. This meant that new techniques would have to be developed for sealing joints in hydrogen ducting. Existing seals could not meet the heavy demands of the fuel. And once again, the state-of-the-art would have to be stretched still further. 10 days later, the stand was repaired and testing continued. In the repeated shakedown of these systems as a unit, cold tests here covered everything short of engine ignition and served as a prelude to the hot firing program at Edwards rocket site. Later, as Centaur flight articles came off the assembly line, S4 facilities were used for pre-flight readiness tests. Meanwhile, the propulsion test vehicle moved to Edwards Test Stand 1-1 and was united with flight-rated engines for the first time. Between February 9th and March 22nd, 1962, 5 hot firings successfully duplicated the in-flight engine sequence. A 280-second test. At that point, the longest dual-engine firing in the Centaur program capped off the first phase of the series. NASA contributed much of its scientific know-how and unique facilities to the Centaur ground test program. At its massive Lewis Research Center in Cleveland, NASA personnel exposed the engines to the vacuum of space. Inside this high-altitude chamber, the engines were put through all operating cycles under conditions almost identical to those expected in flight. The task of building America's first true space-age launching site had meanwhile been accomplished. Next came the job of demonstrating cryogenic handling capabilities, training the crew, and proving the overall compatibility of ground and vehicle systems. The checkout items were Atlas 104D, later used for the first Centaur launch, and C2, then slated for the second Centaur mission. By fall 1961, the exchange was made, and the first flight Centaur was mated with its booster. Before its maiden voyage, a multitude of problems had been absorbed in an intense and diversified ground test program. But still, there was that certain element of chance, that unknown factor that would not reveal itself until the time of flight.
The first flight plan called for an 1,100-mile suborbital trajectory to demonstrate basic functional capability of ground and vehicle systems. Although the primary objectives were not achieved, the results were of great engineering significance. This was the first known flight of an oxygen-hydrogen-fueled spacecraft. The crew, with its facility and ground support equipment, conducted a successful launch, and Atlas lifted the heaviest load in its history. Of the 509 telemetry measurements carried aloft, all but 11 returned usable data on Centaur systems operation. Airborne television and liquid gas sensors provided excellent data until the failure, and thus contributed new information on liquid hydrogen behavior. Breakup occurred at T+54 seconds. Atlas performed perfectly and continued to perform for 2.8 seconds after Centaur failed. A weather shield, which is part of the jettisonable insulation on Centaur, was ripped away at T plus 49 seconds. By July 1962, evaluation and testing had led us to believe that aerodynamic flow around the weather shield produced a net force outward, which was several times greater and in a different direction than expected. Although there is no transonic wind tunnel in this country capable of testing a full-scale Centaur, pre-flight scale model tests and aerodynamic analysis indicated that the weather shield design was satisfactory. The second flight vehicle, however, will carry heavier insulation and stronger attachments. The Centaur weather shield and insulation panels are among several examples of the design challenges presented by liquid hydrogen technology. Centaur is the first to fly with this type of jettisonable insulation.
Centaur is designed for a wide variety of missions. These include injection of satellites into orbits of the Earth, planetary probes toward Venus and Mars, and soft landing vehicles to the Moon. The first few minutes of the flight sequence apply to any Centaur mission. At an altitude of approximately 80 nautical miles, Atlas completes its assignment, separation latches open, and Centaur moves free. Traveling nearly at 9,000 nautical miles per hour, the engines ignite for the first time. Our speed increases to about 18,000 nautical miles per hour, and we enter a circular orbit which can be controlled to lie between 90 and 400 nautical miles above Earth. At this point, we can complete our mission by placing a satellite into a low Earth orbit. But if our payload is destined for deeper space, we can shut down our engines, park at an orbital altitude of around 100 nautical miles, and coast to the proper position for a second engine firing and climb to higher altitudes. The length of this coast period depends on the nature of our mission. During this time, the sun trackers sense our attitude with respect to the sun. The small control rockets point our main engines toward the heat source and shade the tank to reduce internal pressure and hydrogen burn-off. We are now in a position to perform several different missions. The airborne guidance system directs the control rockets to return us to the proper flight attitude and drive us forward slowly. This forces propellants, floating free in the weightlessness of space, to a position for the second engine start. If we want to place a satellite into a circular orbit of the Earth at 19,300 nautical miles altitude, this second firing injects us into an elliptic transfer orbit at 21,000 nautical miles per hour. Then we coast for nearly 5 hours and fire again to rotate our orbit into the equatorial plane of the Earth. The Earth, of course, rotates beneath us during our ascent. The guidance system ensures that we are above the desired spot on Earth when reaching the target orbit. In a circular equatorial orbit, the velocity is such that a satellite always remains over the same point and moves with the Earth in a 24-hour cycle. Now, for lunar or interplanetary missions, the launch azimuth and the parking orbit coast time depend on the launch time and the target body position. Using the 100 nautical mile parking orbit as a typical point of departure, we can cover most of the inner solar system by only 2 firings of 300 and 100 seconds respectively, separated by a coast period of from 2 to 40 minutes. The payload is separated at the proper point in time and space and continues independently toward its target. In the center of the solar system is the Sun. These are the orbits of Mercury, Venus, Earth, and Mars. This line here represents a transfer orbit from Earth to Mars with radar and television connection between the probes and Earth. Another orbit into which Centaur and its payload can be injected is shown here, leading to the planet Venus. Centaur, with a solid third stage of the type used to soft land a spacecraft on the Moon, can also hurl a solar probe to Mercury or inside the orbit of Mercury and get as close as possible to the Sun. This is perhaps one of the most interesting missions Centaur could fly, since the Sun, after all, is the only fixed star that we will be able to reach in the foreseeable future.
In the first half of the 20th century, V2 and the MX-774 advanced us from theory to practical application with successful flights of the first guided missiles. In the second half, we expect to reach the depths of our solar system with instrumented probes, with manned astronomical laboratories, and with manned landing vehicles. Centaur represents the free world's first step in the evolutionary climb toward these goals and introduces basic concepts for spaceships of the future.